Welcome everyone to another edition of the Friday Night Mega Mirror Special. This week, we are going to take a bit of an educational approach to this show, and who better to be our teacher than the smartest man in our community, AB Science. That's right, folks, we are joined by the only scientist I know who actually attempted to build a flat Earth model, and in doing so, proved the globe to be the only viable model, no matter how hard you try to show it otherwise. So if you want to learn something you may not have known before, then grab your drinks, get comfortable, and let the science begin when we come back. And we're back. For those of you just joining us, today we have a special treat as we go back to school and attend a class in reality by our special guest, AB Science. It's going to be an interesting show tonight, so let's bring him on. Hello, AB Science, and welcome. Thanks for taking the time to join us today.
Hello, and thank you for having me on today.
I'm truly pleased that you could make it onto the show. As usual, I would like to begin by asking my usual opening question. How did you get started on YouTube, and what is your channel all about?
This is an interesting one, or at least to me it is. Now, I wanted to do a bit of science outreach, and I'd heard of things like flat earth, woo healing, and anti-vax. So I thought that I would take a look at some of the sillier claims and see what I could come up with. Now, I didn't really want to do a standard debunk video because, well, in fairness, I didn't even know that they were a thing. I wanted to take the ideas and then test them in the hope of showing the general public some of the processes that are followed when we approach different problems. I then dove into YouTube to get a bit more of a feel for all the flat earth arguments, and as up until this point I only heard about the ideas through general chit-chat over coffee in our department, and my God, they did not disappoint in the silly claims department, and I ended up making my first video very shortly after starting to watch them. That's really how I ended up making the videos that I do.
That's awesome. In fact, I don't think I have ever learned as much as I do from your videos. You cover a wide variety of things on your channel, but I think the first one I ever saw was a fourth in a series of videos on basic physics for flat earthers. Some of the math is still beyond me, but I still managed to understand what you were explaining. That's what got me hooked. Let's have a look at that video now.
In the previous video, we looked at the orbit of the moons around Jupiter and derived an expression which is called Newton's law of gravitation. We can now do some experiments to get some information about where we live. Now, there was still a pesky constant of proportionality in our expression for gravity, and we don't know what it is. We could test the force of gravity on Earth by dropping masses and measuring the acceleration, but the acceleration is given by the product of the mass of the Earth, our proportionality constant g, and 1 over the distance from the center of mass squared. Now, we can assume that the distance from the center of mass is pretty much equal to the radius of the Earth, provided that we stay close to the Earth's surface. But we don't know what the radius of Earth is. Now, there is of course the famous Cavendish experiment where we attach two masses onto a rod, which is horizontally suspended using a wire with a known torsion coefficient. The torsion coefficient is a scaling factor for the force that you work against when twisting a wire. We let the rod relax so the bar is in an equilibrium position without any torque due to torsion. Now, torque is the rotational equivalent of force, and it's given by the expression tau equals kappa times theta in the case of torsion, where kappa is the torsion coefficient and theta is the angular separation from the position where there is zero torque. Once relaxed, we mark the orientation of the bar and then introduce a set of large masses as shown on the diagram. If Newton's universal law of gravity is correct, then the masses will exert an attractive force onto the masses at the end of the bar, and this results in another torque given by the expression tau of g is equal to Lf of g, and this torque is associated with the gravitational force. The bar will rotate and the distance between the large and small masses is reduced, but as the bar rotates, torsion is introduced in the wire, which opposes the gravitational force. When you add the two forces together, the equilibrium position has shifted and can be found by setting the torsion force equal and opposite to the gravitational force. So what we get is that tau of g must be equal to tau of t. Now we plug in the two expressions for the forces, so we have kappa theta is equal to L gm1 m2 over r squared, and we can then solve for g. The bar will oscillate about the new equilibrium position for a while, but it will eventually come to rest at its new position. And when we do the experiment, we find that g takes a value of 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared. Newton's law of gravitation is proportional to 1 over r squared. Now this tells us that the force due to gravity is symmetric in all directions. Now this can tell us something about the shape of the Earth and other planets. Of course, we observe other celestial bodies and we see that they are spherical, and therefore we are pretty safe in making the assumption that the Earth must be spherical as well. But the question is, why are they spherical? And why are smaller celestial bodies such as Phobos or Deimos not spherical? Now the answer to this is that the gravitational force of an object acts on itself as well. Once the object reaches a certain size, it starts compressing itself into a sphere as the force due to gravity starts to overcome the strength of the object's material. Each particle then tends towards the equilibrium state where the force of gravity is opposed by the strength of the material. As the forces are radially isotropic, this results in a sphere. The sphere is the most thermodynamically favorable solution to the problem, as each particle ends up in the lowest accessible potential energy state. Now the critical size for this to happen is called the potato radius. A derivation of the potato radius can be found in an essay called The Potato Radius, a Lower Minimum Size for Dwarf Planets, and the link will be in the description. Now this is a result that is observed in nature. All objects above a certain size are spherical. Now we can use our measurement of the gravitational constant to measure the mass of the Earth. Now note that Cavendish didn't actually explicitly state the value for big G in his paper. The Cavendish experiment was actually designed to measure the specific gravity of the Earth. In essence, he tried to weigh the Earth. We can easily calculate the mass of Earth using Newton's universal law of gravitation, but we'd have to assume that the accepted value for the radius of Earth is correct. Or we could just measure it ourselves. Now we can take a rod and stick it vertically in the ground. We then measure the length of the shadow when the sun is directly south. We get a friend to repeat the measurement a few hundred kilometers north or south. Now, as long as we know the distance between the measurements, we can figure out the angular separation between the two measurements and figure out the radius of the Earth, as it is given by the distance over the angular separation. Now, when we do this, we find that the radius of Earth is 6.371 million meters. Of course, this assumes that the Earth is a sphere, but we can justify this assumption by adding measurements, and we can measure the shape of the Earth. Because if and only if the Earth is a sphere with the Sun being far away, then the solar elevation, beta, along a line of longitude takes the form of beta is equal to pi over 2 minus d over r, where d is the distance from the position where the Sun is directly overhead and r is the radius of the Earth. Now we can fit this function to the data where d is our independent variable and r is just a fitting parameter. This will not only confirm that the Earth is a sphere, but also give a more accurate value of the radius of the Earth compared to when we're using 2 points as Eratosthenes did. We know that the force of gravity is proportional to the product of an object's mass and some acceleration. Now, on Earth, the acceleration is the product of the Earth's mass and the gravitational constant divided by the distance to the center of mass squared. Now, when we are close to the surface of the Earth, we can make the approximation that the distance between the object, a few meters above the surface of the Earth, is pretty much the same distance as if it were on the ground. So if we hold an object 1 meter above the ground, we can say that the force due to gravity is the same as if it were on the ground. When we drop an object from 1 meter off the ground, let's say in a vacuum to minimize drag, we measure an acceleration of 9.81 meters per second squared. We know that the product of the mass of the planet and big G over the Earth's radius squared must be equal to that acceleration. So we can rearrange and plug in the numbers to get a mass of the Earth at 5.97 times 10 to the 24 kilograms. At this point, I just want to highlight everything we have covered so far in this series. All we have done is invoke some conservation laws and basic thermodynamics, and using logic and mathematics, we have managed to derive a series of physical theories that we can test. Doing that, we have figured out that the Earth is a sphere, and we measured the radius. We also then managed to figure out the mass of the Earth as well.
That was great. I always learn something new when I watch your stuff. I suppose it must take a fair bit of time to put together a video like that. Can you give us an insight into the process you follow to produce them?
Well, most of the process is actually in the decision of whether or not to cover a topic. I never really thought that I could get away with picking a video and doing a Simon Down style debunk. Firstly, I am not funny enough to make that entertaining, and secondly, there are people who already do that really well. I tend to pick a particular claim rather than a person and then explore it. Sometimes it is just about how the claim is based on a straw man argument, where the flat earther makes a statement and then draws a logical conclusion. The conclusion would usually be correct if the initial statement were accurate. Take the pressure and container thing, for example, where a flat earther may claim that pressure is defined as the force exerted on the walls of a container, and the atmosphere is pressurized, therefore there must be a container containing the atmosphere. Now, there are many issues with this statement, but the most striking is the initial premise. It is not the correct definition of pressure. But I don't really pick a topic because people make a mistake. It has to be an interesting mistake, so something where the correction usually goes into interesting ideas in science, where there's no point in doing this in the hope that some flat earther will actually watch my video, learn from it, and then admit they are wrong. For me to do a video, it has to be something for the general audience to think something along the lines of, oh, I didn't know that, or even better, that they think that that thing that I thought was really complicated all this time, it's not actually that complicated at all. But the videos that I do find most interesting are the thought experiments, the ones where I take a claim and then suspend disbelief and assume it to be true to see if I can use it to make some testable predictions. And these are the videos that attract the most flack from flat earthers. But once I found a topic, it is pretty straightforward. My videos are actually just PowerPoint slides exported to an MP format, and then I have some talky bits.
Another thing I really enjoy about your channel is the diversity of content. You have some pretty advanced science content mixed in with flat earth debunking stuff. What other topics do you hope to cover that you have not covered yet?
Well, there is a long list of things that I hope to discuss every time I kind of think about where to take this channel next. The anti-vax and climate change are always the first bits to pop into my head. Unfortunately, I don't really know enough about immunology to make similar style videos about vaccines, so I'm benching that for a bit. Climate change is something I really want to explore more. However, it is very hard. And at the moment, I'm still going through a series of videos on the scientific approach where I go through different aspects in science in very general terms. I do enjoy this series quite a bit, as it does push me to explore things which I usually take for granted, or cover practices which are not really applicable to my field. In future, though, there are a number of ideas floating around which I may pursue. I am presently exploring some educational stuff and issues in sustainability, and these are a mix of collaborations and solo stuff. We then also have some big changes coming up for the Shields channel, but I won't say much more until everything is actually ready.
That's something I certainly look forward to. But as I was going through the stuff on your channel, I rewatched one of my favorite videos which I particularly enjoyed on setting the record straight on what the scientific method is and how it actually works. Let's have a look.
Flat earthers tend to use very strict and narrow definitions of experiments and the scientific method. It should come as no surprise that this is due to a complete lack of understanding. The scientific method is really simple and rather intuitive if you think about it. It's a cyclical process that goes through observing something or asking a question. This then forms the basis of our hypothesis. We then test the hypothesis by doing things in a systematic way and then analyzing the outcome so we can draw a conclusion. The big thing that I want to point out is that this is a cyclical process, and by design it is vague. The reason for highlighting this is that a lot of the flat earth pseudoscience peddlers will take a very strict definition and usually treat it as a linear process where you must start with the observation of a natural phenomenon. They then conclude that if you deviate from this, then your investigation does not follow the scientific method. The big problem is that this excludes any investigation which starts with a simple phrase of, well, fuck it, let's see what happens when we press that button. The rules are vague because of the wide application. Whether you study physics or paleontology, you have to use the scientific method. However, to approach an investigation in these different disciplines in the exact same way is just silly. Scientists also rarely spend their days thinking explicitly about how their approach conforms to the scientific method, and this is because it is just second nature. Now, and as a result, it may appear like a researcher employs a slightly different version of the scientific method, but when you break it down, the same series of steps will fall out. But let's have a look at the steps. A good starting point is the observation or question stage. Now, the flat earth requirement that there must be an observation of a natural phenomenon is about as useful as a marzipan dildo. It excludes that possibility that there may just be something in the theory that's worth exploring, something we haven't observed, but what the theories or logic predict. A great example of this is gravitational waves. At no point did we observe them, but we concluded that if our understanding of general relativity is correct, then we would expect gravitational waves to be a thing. The same thing happened with black holes, the particles described by the Standard Model, or elements in the periodic table. So in this sense, our observations are predictions made by our theories. Alternatively, we could take conclusions from other studies. For example, we can take a study that shows that meat consumption is lower in rural China, and another study that shows that the incidence of cancer is also lower in rural China. We can then raise the question as to whether meat causes cancer, and then fail to publish on the study and forced to write a popular science book where you can peddle your nonsense to the masses. In case you've missed this, this is a reference to a book called The China Study, which is a load of unadulterated horseshit. But once we have an observation or a question, we can form a hypothesis. A hypothesis is essentially a simple statement which can be evaluated as true or false, or when you delve into the nitty-gritty, you most commonly come up with, well, maybe, at which point you have to rethink your approach. But forming a hypothesis can be as simple as just reframing your question into one of these statements. But there are other ways to go about it as well. In physics, we are now in a position where our theories are not always described by a series of simple equations which we can easily rearrange to form a simple hypothesis. We often come across equations like this one, and I'll give you a few seconds to figure out why this equation is so damn difficult. Now, don't worry if you haven't spotted it, but this equation is called the Landau-Lifshitz-Gilbert equation, which describes the magnetization of a single spin in a magnetic field. The problem is that we have independent variables h and m, and a dependent variable dm by dt, which is also an independent variable. To add complexity, we also have to consider the magnetic field caused by the spin, which is adjacent to the spin, and take into account that we are trying to solve for 500,000 spins at the same time. The result is that we can't actually solve this analytically, and we have to do it numerically, and for this we employ simulations. Now, when doing simulations, we also follow the scientific method. We start with an educated guess based on known results and build a hypothesis along the lines of, well, according to my understanding of the theory, this should happen. When we run the simulations, we get lots of data back, and we can use this data to figure out a relationship between different quantities. Our simulated experiments are then a test of how well our predictions match scientific theory. Provided that all the simulations were performed correctly and a hypothesis evaluates the truth, then your hypothesis is consistent with scientific theory, and this conclusion will then become the hypothesis of the main experiment. And this is the domain in which computational and theoretical physics lives. There are many ideas in physics around areas such as dark matter or dark energy, which are a result of these kinds of investigations. However, these ideas are still hypothetical. Many people, myself included, have published on this process alone, but the key point is that this process generates hypotheses only, and these are to form the basis of further real-world experiments. But now we've established a hypothesis, we can test it. The next stage is often referred to as the experiment stage. However, this is a misnomer, as an experiment has a very strict definition. An experiment is a method where researchers manipulate an independent variable and observe a change in dependent variables whilst controlling for other variables. However, there are more ways in which you can investigate a relationship between the IV and the DV. We can also do field experiments, randomized controlled trials, quasi-experiments, cross-sectional studies, longitudinal studies, case control studies, or combinations of these, but I will cover them in another video. If we take the classic controlled experiment where the experimenter has full control over everything, then the test stage is relatively simple. Note my use of the word relatively. Throughout your experiment, you will have to do acceptance testing and calibration for every bit of equipment that you use. Here, you check that everything works as expected and make sure that you know how it behaves. This could be as simple as making sure that your scales actually give you an accurate reading of mass, or that your electromagnet actually produces the magnetic field that you expect. Each of these steps are mini investigations in themselves, and they have to follow the scientific method. Fortunately, these tests are usually quite simple, but in some cases they are not. There is an entire field of physics dedicated to developing tools to perform experiments, and many PhD students will have spent a significant amount of time building their own apparatus for measuring things. Once you have tested all the individual bits, you are still not done, however. You have to test whether the whole ensemble actually works as expected. And guess what? This involves a whole scientific investigation in itself. But once you think that you have all the data that you're after, you can go to the analysis stage. Simply put, this is the stage where we see if the results match the predictions. Now let's take this equation. And we have this data set. We can then fit this equation to that data set. Now, this in itself is also a scientific investigation and is an experiment in itself, where you hypothesize that the model fits the data and you test the fit. Your independent variables in this are the fitting parameters, A and lambda in the case of this model, and your dependent variable is an objective measurement of how good your fit is. And you will notice that values for A and lambda popped up on the screen along with some errors, and these are useful because these values could represent values which are known, such that we could use them to check our work, or these values could form the subject for further studies. Your conclusions could be as simple as that the model does fit or it doesn't, and on that basis you either accept or reject the hypothesis, or more formally you either reject or accept the null hypothesis. But now you have drawn a conclusion, you can use this to form the basis of the observations for your next go around the cycle. But before you do that, you write everything up and send it off to a journal, or just print it off and throw it into the forest so you can tell your colleagues that you have submitted to Nature. Flat earthers tend to use a really narrow definition of what the scientific method is and what it entails, and it gets portrayed as a simple linear step-by-step process with very strict definitions of what can happen at each step. In reality, the scientific method is very loosely defined and a circular process. Because of this, there is the possibility of infinite complexity. Whereas you may have been taught that the scientific method looks like this, you'll very quickly realize that this is just a fundamental building block. In reality, when you're trying to describe your investigation using this building block, it looks more like this. And this is why it took 12,000 scientists, $13 billion and 35 years to detect the Higgs boson. If you can give a full and exhaustive description of your investigation and it only follows this, then you can be pretty damn sure that your investigation was not done properly.
That was awesome. You certainly showed how wrong flat earthers get it. Who do you think is the one flat earther that is most notorious for getting it all so wrong?
To be honest, I don't really watch Flat Earth videos. Nothing new has come up since I started, and I don't really go after individual videos, so I don't really involve myself with different personalities. Having said that, at the moment, I would say that Sleeping Warrior and that guy, they would stand out to me as they are some of the more vocal creators out there, and it's more their arrogance that makes them so noticeable. But at least with Sleeping Warrior, you can tell that he has at least tried reading up on the topic, even though I still haven't actually seen any evidence that he's read further than the first 2 sentences of an article.
I've also noticed that you have started a news-style segment on your channel. Can you tell us what type of content you will cover in that style, and how often can our viewers expect to see them?
Well, the idea was to cover science, technology, health, and education, and anything related to that, so current affairs may pop up in this quite a bit. I will be trying to release one every month, but there may be the occasional extra as there are some interesting stories happening.
That's really cool. I actually like that format a lot, and you present it very well. For those of you who may not have seen the first edition of that series, have a look.
And welcome to this new experiment for my channel, where I will be covering some science-related stories that have been popping up in the media and the literature. I will mainly be focusing on things pertaining to science, technology, education, and health. There may be the occasional bit of politics, and you can expect me to be impartial roughly 10% of the time. Anything more than that is just a bonus. So we begin with room temperature superconductors. Superconductors are devices through which a current may be passed without resistance, and this means that it would be possible to transmit electricity over long distances without any losses. The problem is that superconductors need to be cooled to below a particular critical temperature for it to work, and this limits the application of superconductors. In May of this year, the record for a superconductor with the highest critical temperature was broken with a material which has a critical temperature of 250 Kelvin or minus 23 degrees Celsius. The catch is that the sample has to be put under a pressure of 170 gigapascals, which is 1.5 million times the atmospheric pressure. In a recent paper published in Physical Review Letters, a Chinese group outlined their predictions based on computer simulations for a superconductor with a critical temperature of 473 Kelvin or 200 Celsius, and this is pretty exciting as it means that there is a candidate for a superconductor which works at room temperature. Unfortunately, the material is predicted to be superconducting only at 250 gigapascals, and although this is achievable in a lab, it does limit the real-world applications, but it is definitely a step in the right direction. The UK's Conservative government has promised new investment in green policies, namely a £1 billion investment in the automotive industry to focus on reducing emissions in the automotive sector. Another promise is to create more green spaces and planting more trees, and a new future homes standard to make sure that new homes are more energy efficient. But there's one very shiny promise, and that is the construction of a nuclear fusion plant by the year 2040. Now, the media is pretty predictable when it comes to their report on this announcement. The pro-Tory press is generally in favour of these measures, and the anti-Tory press is saying that it is not enough. Now, when it comes to the first 3 points, I would tend to agree with the anti-Tory press. It is nice that these policies are announced, but maybe we should be doing a bit more. Now, generally Apparently the press is pretty excitable about the last point though. I mean, who wouldn't be? Nuclear fusion represents the ability to generate massive amounts of energy with negligible waste. Now, there are a few newspapers which have said that there have been some issues around nuclear fusion and that the target may be a bit ambitious, but none have really addressed the reality. The reality is that this is batshit crazy. Now, the £220 million that the government is pledging is very welcome, and it will definitely help advance research in this area, but it is not going to deliver this goal. The first milestone we need to hit in the development of nuclear fusion is to demonstrate that we can actually build a reactor which generates more power than is put in. And this experiment is being carried out in a project called ITER. However, the experiment will not be going live until 2030. If everything goes according to plan. And once ITER is live and demonstrates that it can output more power than is put in, then the next step will begin, which is to build a prototype nuclear fusion plant called DEMO. If everything goes right, DEMO will go live in 2050. Yes, 2050. The Conservatives are announcing that a fully functioning nuclear fusion plant will go live 10 years before the first prototype. The only way that this is going to happen is if the government is really made up of extra-dimensional lizard species with knowledge of advanced alien technologies. Because I have called the Tories batshit crazy, I will take a moment to call Labour batshit crazy as well, because they are. At the Labour conference, a policy was announced to scrap public schools in the UK, and for viewers outside of the UK, these are really private schools, but we call them public schools because Britain is weird. Generally, I am not in favour of private schools in principle. I don't really care if your parents have more money than sense and want to send you to a really expensive private school. My issue is that private schools generally do not prepare students for university as well as state schools, and they also foster quite a bit of cronyism in business. That aside, abolishing private schools is silly. The taxpayer will be footing the bill for buying out private property or having to add capacity to existing overcrowded state schools. What could possibly be a sensible alternative is to take all that money you intend to spend on abolishing private schools and just invest it in the current state schools we have. We can fix the culture within schools so teaching becomes an attractive profession again. We can invest in staff and resources so teachers can actually teach again, rather than drill a list of facts into the student's head for them to regurgitate during exams. With this policy, it's just like the Tories and their fusion power. Labour is more focused on presenting an image to win votes rather than developing sensible policy. However, this move is unlikely to produce that effect, unlike the Tories and their batshit nuclear fusion policy, which may actually do the trick. Just when you thought that the recruitment process wasn't stupid enough, artificial intelligence is now being adopted to make it a hell of a lot dumber. Large companies are using it during recruitment processes. The idea is that the applicant answers a few standard questions whilst filming themselves, and then AI technology will analyze the language, tone, and facial expressions of the candidate. The AI is trained to compare traits against those of prior interviewees who have shown to be good at their jobs. It does have some advantages, as it is not subject to the recruiter's interviewing skills or their mood. However, there are some legitimate concerns about the technology. Unless the AI is trained on a large representative sample, the AI will likely be biased and discriminate against people of different backgrounds. In addition, the AI judges an individual on a short clip, which shows a person responding in an interview situation, and it is not a work setting involving teamwork, although most bad interviews already do that anyway. In other news, in September, the Emery ice shelf has produced a very large 1,636 square kilometer iceberg, which is known as a calving event, and this is where a large chunk of ice breaks off the main shelf in Antarctica. And this thing is going to be a pain in the ass for shipping, but it is not associated with climate change. However, if you are a flat earther, you should be concerned, as a piece of the ice wall has now broken off and the ocean is being drained away. So it is the time of year when the science community is anticipating the announcement of the Nobel Prizes. In this month's Physics World, Hamish Johnston explores the process of selecting who the winner of the Nobel Prize for Physics is. Each year the Nobel Prize winners are announced in October, but the selection process begins in September of the previous year. Nominations are submitted by 3,000 physicists, which include all the members of the Royal Swedish Academy of Sciences and all previous laureates. Then all tenured professors in the Scandinavian countries and selected senior physicists around the world also get a say. Roughly 400 nominations get returned, and the committee comprising 8 scientists sift through the stack of nominations and select roughly 20 of the nominations. The committee then approaches specialists in the field of each of these 20 nominees, and they get reports on their work. The committee then makes a recommendation based on these reports and proposes that to the Royal Swedish Academy of Sciences. Once this recommendation is approved, a report is written about the winners and it will be made public once the prize is announced. The only question then remains is who will win it this month. So that was it for my first quite editorialized news edition. Let me know what you think in the comments section. Is this something that tickles you, or is it a load of horseshit that should just be killed with fire? Let me know.
Well, that's about all the time we have. It's been an absolute pleasure having you here, AB, and it was fun and yet educational speaking with you. Is there anything you would like to share with our viewers before we close out?
Well, of course, I would like to shill my Twitter, which is science_AB, and my Patreon, where you can search for AB Science, and you'll find me there for the occasional extra nugget. But most importantly, go check out the Silly Shill Show, which is a Saturday night talk show I'm regularly involved with, and subscribe to that channel, as lots of exciting things will be happening there very soon.
Fantastic. Well, thanks again for being here. I'm really looking forward to your next video, and we wish you luck with your latest addition to your channel, Nerdline News.
So thank you for having me. It's been fun.
And that about wraps it up for this week. We hope you've enjoyed this week's edition of the Friday Night Mega Mirror Special, featuring AB Science. If you haven't been to his channel yet, please visit at the end of this show. I promise you will be amazed at how much you can learn from the experience. Also, please take a moment to like and subscribe if you've enjoyed tonight's show. And remember to hit the bell for notifications of new content as soon as it's posted. If you would like to help and support this channel, please have a look at our Teespring store, where you can get your very own steaming cup of reason, or a cool t-shirt like mine. Thank you for watching. Until next time, this is Spike signing off. See ya!